I'd like to begin by thanking Andy and Dennis for inviting me to speak today. My first few paragraphs are addressed to the student body, and then I'm actually going to read from my book. The intuition that scientific inquiry and the methods of pure mathematics may yet lead us into the light of certainty is to be trusted. The doubts of the past century have led us to a crisis that undermines the scientific endeavor. Despite the disquieting failures of modern logical methods, we must regain our confidence, cease to be enamored of our successes, and accept the challenges that remain. For us to succeed, however, requires that we better understand the relationship between the disciplines of pure mathematics and the physical sciences. Most of all, it requires that we be bold. Sustained by humility, we must maintain a fear of dogma and have the courage not only to challenge intellectual taboos, but our own intellectual investments. There is great difficulty in pursuing basic research that must, by necessity, take you from the comfort of consensus into the realms of our collective ignorance and false interpretations. The great advances of one civilization over another does not arise in the inevitable application of new discoveries. Investments of a few years or months in the developments of new technologies offers only a transitory advantage and the comfort of security to a temporary elite. They are the trinkets of basic discovery. Great advances and great civilizations arise from the deeper understanding that requires both the liberty of intellectual pursuit and time. Neither are dependent upon private funding nor government grant. They are the sole product of the human spirit, the independent mind, and the defining commitment of the inquirer. I read now from my forthcoming book on the origin of experience. There is a broader historical context here that I can present today, and I now only mention it briefly. In it, we find a precedence for the treatment of logic as a natural science, whose mandate is to build the bridge between pure mathematics and the physical sciences. This view was clearly articulated by the great American mathematician, Benjamin Peirce, the father of Charles Sanders Peirce and James Mills Peirce. The circumstances are those of the 19th century that saw the development of scientific inquiry and higher education in the USA. The narrative occurs especially around the birth of Harvard University. It is to be regretted that the majority of you here will not know of these circumstances or these names. This period has nonetheless informed America's greatest minds, and I have come to call it the American Enlightenment. I defer all defense of this narrative to my lecture on January 15th in this forum on the life and work of Charles Sanders Peirce, who died in 1914. I also regret that I do not have the time here to relate the mathematical approach I describe to the evidence in biophysics, or to walk through the mathematical details present in the book. My content selection, that amounts to the opening pages, is intended to provide an accessible overview of the approach. However, as a punchline, I will write the equations I describe on the blackboard. I I will read until approximately 5:15 and then take questions. I have no doubt that in this forum, you will have questions concerning my exclusion of Turing computation from biophysics. Those are not adequately covered in this content. I will be happy to defend this position at the time. I hope also to get questions that relate to the practical implications of the ideas presented, their implications to machine engineering and medicine, for example. The book is entitled On the Origin of Experience, the Shaping of Sense and the Complex World. And it begins with a quote from Benjamin Peirce that reads, "In every form of material manifestation, there is a corresponding form of human thought, so that the human mind is as wide in its range of thought as the physical universe in which it thinks." But how are we to explain the presence of our experience in the world and its many forms? This book is the product of a research journey to answer these questions that begins for me in the corridors of the University of Arizona in conversations with the mathematician Roger Penrose. In March of 2003, we participated in a meeting that asked whether advances in quantum mechanics and biophysics informed us concerning the nature of the mind. Relying primarily on the work of Kurt Gödel and Alan Turing, Penrose argues that a mathematical solution to the problem describing experience in nature is impossible. More precisely, he says, the solution deals with the non-computable. It has always been my intuition, however, that the limits of logical description that he refers to are not limits of the world or failures of mathematics in general. They are rather indications of a failure in the foundations of mathematical logic. They are failures of a particular method. It seemed to me, therefore, most likely that resolution could be found by an inquiry into the nature of computation. I am especially concerned that the immediate, continuous transformation of structure, as holistically conceived by a mathematician and evident throughout biophysics, is not reflected naturally in any of Turing's methods of systematic computation. This fact passes unnoticed at the scale of computing familiar to most of us, and this has seduced many to believe that computation is invincible. But it is now clear that the efficiency of the Turing computation decreases as the problem size increases, with physically limiting consequences at large scales. These consequences will ultimately lead me to exclude Turing's models of computation from biophysics. As a keen scholar of recent biophysical results, funded for other causes often far from basic research, I had long suspected that the attempt to mathematize biophysics promised to inform the foundations of logic. It seemed to me impossible for biophysics to make progress without an exact account of experience as sense. And so as I listened to Penrose's ideas and concerns, a contrary approach to the problem came to mind. My approach then is simple to state. It is to ask what methods are required to enable a mathematical description of the different forms of sense, how they are modified, and the role that these actions play in the operation of biophysical structure. Sense, in this case, is simply the variety of experience. Specifically, the goal of such an approach is to illustrate how a particular sensation is formed and modified in biophysical structure, and the role that this action plays in the selection and performance of directed and non-directed response. And further, to describe how this basic mechanism combines to construct the entire experience of individuals and the operations of the familiar mind. Such an approach is the first step toward reasoning about the many forms of sense, its place in nature, and in the considerations of physical science. It leads us to ask what may be missing from our physical conceptions and models of mathematical computation. With respect to these conventions, it asks, what remains for the living mind? In addressing this question, I illustrate in exact terms how my solution takes its place in the physical sciences. The purpose here is to present the theory in sufficient detail to a broad audience, across disciplines. It includes the mathematical framework of the theory and its immediate implications to physics in general, logic, and computation. As a consequence, I treat logic as a natural science, whose mandate is to build the bridge between pure mathematics and the physical sciences. New section entitled Experience as Sense. I begin by clarifying and stating informally, as clearly as I may, the subject that concerns us. It is the origin of experience, its formation and shaping as sense, and the role that this action plays in biophysical mechanics. It is the shaping of all complexity. When I speak of a complex world, I speak of biophysics in particular, and also more generally, the formation and behaviors of the living world and all that derives from it. What is experience? It is certainly the senses and ideas that are forced upon us by the world. But this view alone is insufficient, for experience is equally found in the sensations and ideas that we force upon the world by our actions. More generally, experience then is that which is most familiar. It is common to all sense. When I speak of experience as sense, I speak of its variety in individuals. These experiences include the textbook senses, vision, the sense of aroma, touch, taste, and sound. It includes the experience of pain that turns out to be an entirely independent and specialized sensory system. It includes the sense of ourself and the behaviors over which we may have the power of veto. It is then, in the most general terms, in our anticipations, recognitions, and actions. It includes all that we speak of as thinking, intuition, and emotion as forms of internal sense. This is the experience of our own structure and its operation. Ideas, feelings, and passions of all kinds are such experiences. Experience dominates our actions and is modified by our physical form. We are each aware that our experience and behaviors are modified by the physical effects of trauma, sickness, and intoxication. Our decisions concerning how we move about the world, where we locate ourselves, with whom we share our lives, our pleasures and our discomforts, are dominated by the entirety of our continuing experience. I will also assume that it is, by the necessity of a mathematical approach, present in the varieties of sense not seen in our species. For example, in the sensory and responsive mechanisms of plants and other organisms. Now let me be clear, I am not suggesting that the form of sensory experience in plants and bacteria is anything that we would recognize as our own. The experience of each species has a unique form. Nor am I going to suggest that inanimate objects think and feel. I'm simply saying that if we are to develop a mathematical foundation for a general theory of biophysics, all sensory and responsive behavior must be given the same basis. There are two principal factors that distinguish biophysics from the inanimate world. The first is that sense and response are bound in the function of flexible closed structures such as you and I. The second is that the basis of these functions, the basis of experience, is a universal effect in such structures. And so it is that the challenge here is to determine the role of that effect in exact terms. I am aware that many of you, including some fellow scientists, still consider experience to be the exclusive domain of our species. Our intelligent behavior does, in many ways, exceed that of other organisms that have appeared upon our planet. This capacity for higher intelligence is no doubt enhanced by factors other than experience. These factors allow us to succeed where other species that may well have a richer natural experience do not. I'm thinking here of creatures such as dolphins, whose brain, we may argue, exhibits a greater refinement and sophistication of structure than our own. The factors that give us advantage include our capacity to finely manipulate physical objects and record, our capacity for literature, and our ability to develop and conduct scientific inquiry over generations. This advantage is confirmed by our surprising ability to manipulate the world such that we may imbue machines with aspects of this intelligence. But that this is indeed the case says nothing at all about experience. It provides no cause for the assumption that other organisms do not share it. New section entitled, What the World Is and How We May Speak of It. The epistemic cause, what the world is and how we may speak of it, finds great advantage in the development of pure mathematics. Indifferent to the acts of physical science, pure mathematics is the science that draws necessary conclusions from premises of any kind. Yet it is the judge over all of our ideas, and physical science may not be indifferent to it. In the epistemology I present, I will speak of necessary distinctions and ways of speaking. A necessary distinction is a distinction that we force upon the world while a way of speaking is a distinction that the world forces upon us. In other words, many of our conceptual devices in science and elsewhere are free inventions of the mind that enable us to speak about the world. The world itself, however, is free of such devices except in this form. These basic concepts are fundamental to both the biophysics of experience and the epistemology presented. I avoid the vernacular ways of speaking about the epistemic cause with some deliberateness. I later provide a more general theory of knowledge and information than that which is typically found. New section. How to mathematically characterize a sense. At this point, allow me without further ceremony to address the most significant question that arises from the discussion so far. How? exactly. May we characterize experience as sense. It is perhaps surprising that the epistemic considerations and mathematical devices advocated by Einstein provides the way forward. I will refine Einstein's approach in order to meet my goal. This requires, however, that I defend Einstein from well-known criticisms in the literature that are yet to be resolved definitively. I will also need to make my use of this approach clear with respect to modern theoretical physics and biochemistry. I briefly state the case here in terms that are perhaps familiar. I elaborate and clarify as we go. If you have more than a passing understanding of general relativity, as I hope many of my readers do, then the following states the case plainly. Later, I provide an exact formulation. However, we have some groundwork to cover before I do. As a word of caution, I must note that the modern presentation of general relativity that often neglects the epistemic questions may not serve our understanding here. I rely primarily on Einstein's original writings on the foundations of general relativity, published in German in 1916, and his writings in the period immediately following. There are two central components to Einstein's view. The first is the equivalence principle that in its naive form simply states that inertial and gravitational mass are equivalent. Further, after some consideration of this principle, we get affirmation of a universal unity, such that all the laws of nature have a single source. This leads to an important question, however, concerning the nature of this source, the essence of nature, and how to speak of it. It is in the light of these considerations that Einstein advocates that all the laws of nature are to be characterized in a generally covariant form. He says, the general laws of nature are to be expressed by equations that hold good for all systems of coordinates, that is, are covariant with respect to any substitution whatsoever. This is his definition of generally covariant. The epistemic consequence of this view is immediately recognized by Einstein. It is that space-time is to be isolated to its epistemic cause. As Einstein puts it, this requirement of general covariance takes away from space and time the last remnant of physical objectivity. In other words, space and time are to be simply treated as convenient ways of speaking about the behavior and structure of the world, independent of considerations of essence. My agreement with Einstein will lead me to advocate a form of structuralism. This view simply states that the subject of both pure mathematics and the physical sciences is structure. Pure mathematics and the physical sciences are to be considered to have the same subject. Therefore, if logic as a natural science is to build the bridge between the two, its subject must also be founded upon this structuralism. This acceptance of general covariance as the basis of a logical and mathematical construction of the world recognizes the limits of discovery. If nature may be fully described by the effects of covariant essential properties, then the basis of these distinctions, the essence of the subject, is inaccessible, except by our direct experience of the world as its part. This is then the direction that I pursue. By it, I am able to describe the mathematical framework of a physical theory in which the essential properties of nature include the basis of experience and provide a general theory of biophysics that includes the effect of this basis as sense, in addition to the formation and operation of all biophysical structure. New section. Experience as an essential property of the world. The goal of such a formulation is then not only to enable a means to characterize a particular sense and its developing response potentials, but also to characterize basic and complex biophysical functions of all kinds. This includes the formation of receptor clusters and motor functions upon the surfaces of cells. It includes the basic functions of cell division, and more generally, how biochemistry and biophysical structure work together. It includes the collaborative action of cells and cell types. It includes the action and sensation of musculature and the collaboration between astrocytes and neurons in the brain. A successful formulation will allow us to consider the behavior of organisms of all kinds, from simple bacteria to whales. So it should be clear that I propose a single effect that acts throughout biophysics, one that will not only explain what remains for the living mind, but that will also explain the beating heart. And clearly I must account for why it is that the common basis of these diverse behaviors have different experiential characteristics, why it is that the heart continues by the same means, but rarely intrudes upon the unity of our immediate experience, and why it is that these actions are not adequately explained by known biophysics. For some readers, it will, no doubt, be clear at this point where I'm headed. This unification of a broad range of diverse observed behaviors by a single conception is familiar to all that know science. It is precisely the discovery of Isaac Newton that is so ably refined by the work of Einstein. I am then to propose a single universal essential property that has many of the characteristics of gravitation. Indeed, it is a sibling of gravitation, an essential property of the world. And while the effect of gravitation is most evident in the open structures of the world, the effect of this essential property is seen in the flexible closed structures of the world, such as you and I. It is for this reason that we are informed by Einstein's epistemology. Einstein would enjoy this approach for its simplicity. It is exactly the kind of simplicity he often spoke of. New section entitled Building on Einstein. I have no doubt that some readers will immediately ask how I may justify taking a mathematical construction concerning the universal effect of gravitation and apply the very same techniques to the difficult question of experience in nature and associated behaviors in biophysics. There is a more general question here concerning how it is that mathematics is so unreasonably effective, such that its forms may be applied throughout the natural sciences. I address the relevance of this question in more detail later, but briefly, it is simply that the world maintains a profound uniformity. And this uniformity is evident in the discovery that pure mathematics remains effective independent of scale. So it is that the mathematics of general relativity may also be applied to biophysics. For the same reason, the adjustment of scale in physics, called renormalization, is an effective technique. It is also why small-scale machine computation maintains a useful effectiveness despite its practical limits at large scales. The efficiency of computation is not scale invariant, and we will discover that this is the primary distinction between computation as we understand it today and the natural computation of the familiar mind. If our purely mathematical tools, however, did not demonstrate this effectiveness, then the world does not possess the profound uniformity upon which science relies. In addition, I will rely on this scale invariance to reason about sense in the large and small. It is, for example, why I, almost twice the mass of my wife, have, in all important respects, the same experience and capacities as she. However, I must note that Einstein's epistemology is rarely given the consideration that it deserves. It has been subjected to some derision. Einstein was exhausted in its defense, and it is entirely ignored by quantum theory. Its broader impact is unappreciated even by the intimate friends and admirers of Einstein, including Kurt Gödel and Rudolf Carnap. This is rather unfortunate, because in their own inquiry, it is exactly what they were looking for. Meeting resistance, and in order to communicate effectively his primary physical ideas, Einstein frequently diluted his epistemic statements in the greater cause. This difficulty is compounded by the fact that he does not rigorously apply his advocated epistemology to the formulation of his equations. If Einstein made an error in general relativity, then it is that his equations do not speak clearly of space-time curvature in a way that is consistent with the epistemology he advocated. This led quickly to the accusation that his theory is physically vacuous. The dominant materialist view, in which matter has epistemic primacy, naturally led people to see Einstein's gravitation as the product of matter and to ignore the full implications of the equivalence principle. It is, in fact, not that gravitation is the curvature of an existent space-time, but rather that the effect, an essential property of nature, may be conveniently spoken of as space-time curvature. Despite what now may be viewed as the penetrating clarity of his epistemic stance, Einstein thought of himself as a type of unscrupulous optimist on the subject. In his later years, he put it this way: science without epistemology is, insofar as it is thinkable at all, primitive and muddled. However, the scientist accepts gratefully the epistemological conceptual analysis, but the external conditions, which are set by the facts of experience, do not permit too much restriction in the construction of the conceptual world. Einstein continues. The scientist, therefore, must appear to the systematic epistemologist as a type of unscrupulous opportunist. He appears as a realist insofar as he seeks to describe the world independent of the acts of perception, as idealist insofar as he looks upon the concepts and theories as free inventions of the human spirit, not logically derived from what is empirically given, as positivist insofar as he considers his concepts and theories justified only to the extent to which they furnish a logical representation of relations among sensory experiences. Einstein was aged 80 at the time he gave this response. So it is that by this time, more than 30 years after the publication of General Relativity, he claimed his victories, and the epistemic cause was one he no longer chose to fight. It is my impression that he was simply exhausted by the defense of his epistemological ideas in the face of a stubborn materialism, perpetuated by quantum theory. The epistemic battle over general relativity centered upon the physical basis of gravitation. Since Einstein claimed that space-time is to be restricted to its epistemic cause, this immediately presents the question of what it is that gravitation has an effect upon. What can it be? And he concluded, but the real existence of space and time. And this is where the confusion arises. I propose a simple and perhaps naive solution to this problem that will no doubt be controversial, but, as the English say, in for a penny, in for a pound. The embrace of Einstein's 1916 epistemology has interesting consequences for the formulation of physics in general and the foundation of mathematics. It will enable me to place the basis of experience and the study of experience as sense in exact terms in the physical sciences. By reformulating Einstein's equations to meet the strictest application of his advocated epistemology, the arising structuralism suggests provocative solutions. It will also lead me to argue that this structuralism, founded upon a unity of premises suggested by Einstein's general covariance, is to be preferred in general over the normal axiomatic method. My restatement of general relativity does indeed isolate space-time to its epistemic cause. It also provides an obvious unification of the principal equations of special and general relativity, and provides an account of light as the physical basis upon which the gravitational effect rests. So I trust that I will be forgiven my own unscrupulous opportunism as a systematic epistemologist in order to illustrate my cause. In defending Einstein, I will take this liberty and by it offer a plausible reinterpretation of physical results. In this cause, I rewrite the Einstein equations in a way that allows me to illustrate exactly how a complete theory of biophysics may be incorporated into the physical sciences. In addition, this formulation will serve to illustrate how the structuralism I propose may be broadly applied. This methodological illustration of how a theory of experience may be included in the physical sciences is my sole purpose. It is not my goal to propose a grand theory, and although I must take this excursion through cosmology, my focus is the biophysical matters at hand and the characterization of the mechanics involved that must eventually include biochemistry. New section entitled The Mathematical and Physical Approach. To summarize then, as Einstein advocated, the conception of space-time is to be isolated to its epistemic cause. It is a convenient way of speaking about the generally covariant effects of nature's essential properties. The essential properties of the world are to be identified, and their effect in the world is to be characterized as generally covariant. Further, following Einstein, all the laws of nature are to be of this form, and all of its constants are to be so derived. Our mathematical and physical subject is then structure, and matters of essence must be deferred to our experience of the world as its part. By this means, I can speak of a universal basis of experience as an essential property and its covariant effect throughout the world. Of special interest is the effect of this basis in the flexible closed structures of biophysics, where the effect is manifest as sense and biophysical response. It is the formation of flexible closed structures that makes critical uses of the essential effects in biophysical structure. And it is these effects that form sense and response. Indeed, by this formulation, biophysics becomes the general mathematical science of flexible closed structures and their composition. Let me clearly state now, with the fullest justification to follow, the essential properties of the world by this formulation. The gravitational effect is readily accepted in this role and is well justified by general relativity. In my reformulation of Einstein's equations, I interpret the constant measure of light to adequately justify a claim that light does not in fact move. While there is indeed a covariant effect between matter and gravitation, gravitation is able to self-generate the effects that Einstein's equations suggest, despite of the absence of matter. It will be important for us to consider the end cases involved. This will allow us to recover quantum theory, although we require a quite different cosmology. It is only the light field, free of gravitational effect, that can be said to be without mass. The remainder of the world is composed of gravitational mass and inertial structure. This idea is counterintuitive to the modern mind, raised to interpret light itself to have motion. But this result may be directly derived from the equivalence principle and Einstein's equations. Let me emphasize that I have not set out here to rewrite physics or to propose a grand theory. It is my purpose here only to follow the necessary conclusions of Einstein's methods in order to illustrate how a complete theory of biophysics, including experience as sense, may be formed. Having now spent some time with the idea myself, I find it compelling. It explains why light is constant and without mass. And it should come as no surprise that all the forces of nature may be unified by a conception of light. Mathematically, it may be considered a field that is a universal constant upon which the gravitational effect can act. In speaking of light as a velocity, we are merely referring to the motion of inertial mass within the light field. And we are not speaking of light itself. I show how this view is suggested by Einstein's equations when strictly combined with his advocated epistemology. By this new interpretation, light is to be considered a constant finite field that takes the place of any conception of an existential space-time in the field equations of general relativity. All motion within this field is that of structures containing inertial mass moving within it. All measured mass is to be considered to have a value unified by the equivalence principle. It is always the combination of intrinsic mass determined by structure and gravitational mass. And this will turn out to be disruptive to our notions in quantum theory. But my goal is to speak in the very simplest terms. However, I will seek reconciliation with quantum theory by treating it as a second-order consideration as structure. Structure that has arisen from the simplest, albeit impossible, ideal state. This ideal state, one of the cases that I referred to above, is impossible because there is no circumstance in which we may consider the total absence of the gravitational effect. By this, I mean that the gravitational effect, as characterized by general relativity, and now upon the proposed light field, produces all mass energy in its variety of forms in structure. The light field may now be substituted into the field equations of general relativity. It replaces the conception of an existent space-time that may yet be retained for its epistemic cause. It is then structure bearing mass energy that moves through this field. And wherever there is a gravitational effect, there is gravitational mass, a distortion of the light field. From the standpoint of our current quantum theories, this simply says that all particles have mass, and that their intrinsic mass is a function of their structure, and their measured mass is a function of their intrinsic and gravitational mass combined. With this step, we can unify the well-known equations of special relativity, the equation of mass-energy equivalence, with the gravitational field equations, such that we can determine the mass-energy value of any point quantified by the actual quantity or area of distortion of the light involved. This is difficult enough. Let me note, in keeping with my primary subject, that when I speak of difficulty, I'm always speaking of the absence of familiarity. And this idea of the constant and unmoving light field is certainly unfamiliar. I will be surprised, however, to discover that it is novel. I have little doubt that it can be found somewhere hidden in the private language of theoretical physics, for it is an obvious and literal interpretation of the equations that include light as a constant. More difficult is now the claim that the basis of experience is of equal standing, that it too is an essential property of the world. So let me be clear. While the gravitational effect is evident primarily in the open structure of the world, the effect of the basis of experience is evident in the flexible closed structures of the world. These flexible closed structures are the cells and membranes of biophysical structure. They are organisms, such as you and I. These flexible closed structures exist in environments in which, all things being equal, gravitation places constraints, but does not disrupt the construction and action of these structures. Similarly, the basis of experience cannot be said to produce the familiar characteristics of biophysics, sense and response, in environments or structures other than this. By this conception, I take the equivalence principle seriously as an indicator that nature has just one source for all of its effects, and the properties of this source are these distinctions: gravitation, light, and the basis of experience. Of course, I appear to have left a familiar subject unanswered. This is where matter fits into this model. Here, matter that can be accepted, where that we may accept, is a subject described by quantum theory, is a second-order consideration. In other words, all mass energy in all of its forms is the product of the gravitational effect upon the light field. It is derived from gravitational mass. I give the mathematical account of this later. Briefly, once again, this approach provides us with a route into the standard model of physics and classical forces. For now, let it be sufficient for me to say that all structure and all of its behaviors, including those of biophysics, arise from the generally covariant effects of nature's essential properties. We will learn much concerning the structure of the universe by considering the end cases of the gravitational effect according to this model. The extreme case of the gravitational effect, in Einstein's terms characterized by the greatest possible curvature of space-time, produces a well-known event, the black hole. This then provides the circumstances in which structure appears in the world, is initiated, and from which all matter is derived. It should be clear that this view is contrary to the conventional view and puts matter first, and that makes matter the source of the gravitational effect. This model takes the inverse position. But with this exception and a revised cosmology, the rest of physics stays intact. So this is the model that I wish to mathematically characterize. Much as Einstein did, I prefer the very simplest mathematics. The universal effects of the essential properties are to be characterized as a covariant tensor field, much as we do in general relativity today. However, in the case of the basis of experience, dealing with the effect of this field in flexible closed structure, I make use of holomorphic functors and hyperfunctors to speak of the effect of this field in sense and response. These are holistic structures that act at once and together under the unifying effect of the essential basis, and they will allow me to reason about biophysical behaviors in general. And then it is within this framework that I must devise the means to reason about biochemistry also. I consider the formulation of these functors in terms of modern complex analysis and an experimental geometry that may better suit the task. In the second volume of this series, I compare these approaches in detail. It is worth observing that at this point, that Einstein himself spent a good deal of time, 40 years it is claimed, developing complex analysis as a means of unification. In less formal terms, this mathematical model allows me to speak of the shaping of sense upon the surface of flexible closed structures, or composites of such structures, and the response potentials that develop dynamically within. Systems of these holomorphic functions allow me to consider particular and collective sense structures as non-local integrations of such functors, a collection of dynamic shapes in the organism. This then gives me the means to mathematically characterize not only a particular sense, the dynamically covariant response potentials in the structure, but also combinations of these structures forming higher order experience, and eventually the basic operations of the mind. The mechanism is general, and so provides the means to reason about the full range of biophysical behavior from the smallest to the largest organism. The effect described in physical terms produces a living collaboration between the biomechanics of flexible closed structures, the cells and membranes of the organism, the enclosed biochemistry, and the environment. A particular sense is formed in a particular structure. It may be considered a shape upon the surface of the cell or membrane structure. Wherever this shape occurs, independent of scale, there is precisely the same sense. Latent receptors are induced upon this surface so that the shaping will more readily conform to its stimulus. This mechanism is the basis of the development of memory and habit. This action refines the responsive form of the structure so that response potentials may be said to form under the same effects. In the very simplest cases, in organisms such as bacteria, this occurs upon the opposite side of the closed structure. But it should be readily apparent that such surfaces provide a large combination of potential formations. And so it is that biophysical response is diverse and adaptable, developed in its environment, in the early stages of development and adult plasticity. The book will be available next year. I finished reading for now. What I'm planning to do at this point is just quickly write onto the board some of these equations in a way that is generally accessible. So we can rewrite Einstein's equation, it's well known as a special relativity equation, like so. Okay? And And so now that I'm claiming that there's this static finite light field, we can add into this equation a nonlinear equation G, which gives you the unification of special and general relativity. This, of course, is a very limited equation because nowhere in it does it really talk about structure. So what you sort of want to do, and this is not adequate, let me hasten to add, is add structure on one side and the basis of experience on the other side. So you would have the essential properties of nature in an equation like this. But that really is viable as it currently is formed. So let's talk about those initial conditions. So the light field, the simplest unit for me is the sphere, the unit sphere. The light field then considered to be such a sphere. If you apply this equation to the surface of this sphere, you end up with, this is an ideal state, or purely mathematical state. This is not something that is possible. But if you apply this, what you would find is you'd end up with gravitational mass all around the edge. Okay? And it's this gravitational mass that then sort of reduces to black holes, which generate your structure, blah, blah, blah. Okay? So very different sort of cosmological view. And I'm only really following this because it seems to be just the necessary conclusions of Einstein's method. So by this means then, you can think of this as the force of gravitation on the sphere. And then, of course, you end up with your structure and you get the whole of general relativity. Now, what is it? These are equations of open structure. There's no closed structure at this point. So where we need to take this is into the holomorphic functions, and what you end up with is a holomorphic function that looks something like this. Forgive me if you're not familiar with complex analysis. And in essence, what you have here is a holistic function that describes a shape on the surface of the structure. So in bacteria, for example, this is the function that describes the construction, the development of latent sensory receptors. And here, this would be your motor function. So this is the response. So what you end up with is sort of classical holomorphic hyperfunction between sense and response. Just very briefly. Obviously a lot more to say. That's what I have time for right now. I'm happy to take questions.
I want to go back to the very beginning. There's a claim, a very interesting claim, and go related to a book of the last century, which is sort of interesting. Julian James and the Evolution of the Bicameral Mind, which is at some level a claim that human consciousness has changed in the span of recorded history. Peirce is claiming that humans as of 1870 were capable of the whole universe at some fundamental level.
Indeed.
I don't see how you get there.
Well, why not? I mean, the reason you have that bias is because of 20th century conceptions.
No, I don't believe it's.
I mean, it's certainly an optimistic view on the part of Benjamin Peirce.
Well, I don't know that it's true now.
Well, if it's true, it's always been true. Right? I mean, it's not that The claim is simply that the human mind can conceive of ideas that are sufficiently broad to accurately characterize the world. And that the route, and Benjamin Peirce was one of the founders of pure mathematics, and Peirce is simply saying the route to that is pure mathematics. Admittedly, I mean, it would take some demonstrating, but if we had a theory, say, that explained, the mind, the living mind, and all biophysical behaviors, then wouldn't we be close?
I'll grant that, but there's an if right there.
Well, I mean, I make a rather broader claim, actually, in my introduction, which is to say that it allows us a conceivable certainty. And I go to some length in the book to speak about how it's possible for us to develop a purely mathematical physical theory that is remains falsifiable, but it is of such standing that it lasts for all time. And that's a conceivable certainty. There's a caveat, you have to rewrite mathematical logic with Einstein's epistemology in mind, the structuralism I'm advocating, and the necessity to throw away the materialist conception from which everything we know is founded in some material basis, but to accept that the essential properties of nature are generally covariant, as Einstein said. That's actually I've got some key points there, but this is, incidentally, this is Benjamin Peirce, 100 years or so before our friend Einstein. And this is a picture I rather like at the moment, but I'll talk about this picture and other stuff related to the Peirce family in January. This chap here, with his arms crossed, is Benjamin Peirce. Gentleman in the middle, I hope you recognize, is Abraham Lincoln. And this is not Dan Dennett. It's actually Henry Gould. Joseph Henry. This is Agassiz. Agassiz, 4 of these are Harvard luminaries. Harvard luminaries, they are members of what was called the Scientific Lazzaroni, who founded the Academy of Sciences. But anyway, let me move off of that. That's more historical context. The historical context is essentially here that Benjamin Peirce had a similar idea to my own. And he charged his son Charles with the task at hand. And his intuition was that the recently invented Hamilton quaternions, which is the foundation of complex analysis, was the way forward. Actually, Charles tried to pursue that route and abandoned it. His older brother James, who died in 1906, died the world's expert on quaternions, although he never really published on this subject, for, I believe, social reasons. Benjamin was a professor at Harvard for 50 years, and James was also a professor at Harvard for 50 years. It's an interesting story, which I'll relate on the 15th of January. Any other questions? A lot to take in.
Well, I'll make a comment. I think I probably came in on a subject and I didn't take any of the prerequisites.
Okay. Oh, is that how you feel right now?
That's how I feel right now.
Well,
And
that wouldn't be surprising.
yeah.
Yeah, I mean, the book is obviously goes into some more depth, but what I in here is sort of a in-your-face introduction of the basic idea,
Yeah.
the overview of the overall concept.
But I'd like to know the prerequisites that I should take. Probably so.
There might not be, there might be any. I mean, in mathematical terms, I will discuss, later in the book, I discuss two rigorous approaches to reasoning about cell formations and structures. And I use classical complex analysis, which has developed over the past 100 to maybe 200 years at this point. It actually went out of favor when James Mills Peirce died in 1909. Quaternions and complex analysis were really out of favor, and the new vector analysis had really started to take over. In the past 20 years, I guess, 15, 20 years, complex analysis has come back as a subject of interest in all physics. So in general, I think understanding a little about holomorphic functions, how hyperfunctions, which is the combination of these holomorphic functions, works, that would be relevant from the point of view of the mathematics involved. I am actually going to suggest a new geometry. It's a sort of experimental geometry, because there are some questions I have about the broad applicability of complex analysis for this purpose. In terms of the epistemology involved, which is what people like to call, how we know anything about the world, I actually introduce a broader information and knowledge theory, which sort of more generalizes theories of knowledge. So, an understanding of basically what a theory of knowledge is, what it might look like. And then, I guess, structuralism, which is actually a well-discussed subject. This is a refinement of existing structuralist approach. In essence, all that we can talk about in the world, it says, is structure. Now, there are a couple of forms of structuralism out there in use in science today, if they use an epistemology at all. This is sort of the crisis that I talk about at the beginning, is that science has ceased to adhere to good theories of what in the vernacular we call good theories of knowledge. And so this argues the case very strongly for a structuralism that is founded upon the covariance of nature's essential properties as generally covariant. And the argument is that this is actually a more effective method and to be preferred over the normal axiomatic method because it binds premises. And this was what Einstein was advocating. This is what Einstein advocated in 1916 and all of his work on the foundations of general relativity. And of course, he sort of was railroaded. He immediately came into criticism in 1917. I want to say Kurtzman, or I don't remember the name offhand, who claimed that Einstein's theory of general relativity was physically vacuous. The consequence of that, as I said, is that we have come to invent or endow an existential status for this notion of space-time, which Einstein spoke very strongly against. And of course, Einstein isn't the originator of that idea. That goes back to Ernst Mach at the end of the 19th century. So the precedence for this is historical, in fact. There's not a lot of current curriculum stuff that you would, apart from things like complex analysis, that you would find this kind of view advocated. In computational terms, bring it back in this forum, there are reasons why. I mean, my base career is computation, and the reason I exclude, since nobody's asked me, I'll ask it myself. The reason I exclude Turing computation has to do with the pure pragmatics. The human brain, here's how the argument runs, the human brain dissipates 15 watts of power under circumstances that are quite extraordinary. The distribution of temperature across the brain is within 1 degree everywhere. There are no hotspots. Any computer scientist should be alarmed at that. Right? And neurons don't do what the neural networks guys want you to believe. Right? Neurons work together with astrocytes to change blood flow. They change structure. That's what they're doing. So if you do the computations, right, and you do the calculations, so this is our favorite number right now, right? We want to build computers that are this big. And our estimates, and the claim is I believe it's a completely spurious claim, but the claim is this is comparable to the number of connections in the brain. Nonsense. Because that's not what's going on. So if you do the math, by the way, this requires you to have, in a human brain, only 4 electron volts per operation, per transport, per storage. Not possible, just no way. Okay. So that, and this beast, if we ever get to build one, is going to cost you 16 megawatts or so. Just, all right, so this is the argument, it's a pragmatic argument, why Turing's models of systematic computation are necessarily excluded from biophysics, because there's no way in hell you're ever going to build a machine with that power profile, 15-watt power profile. Just not going to happen. So that's sort of where that argument comes from. And you get a few people push back and say, well, what about reversible computation? Well, this is the notion that you can actually get away from doing something for nothing. I just point people to the work of John Dean Norton at Pennsylvania, who has written adequate papers to show that that's not possible. Landau's principle and all of that. Yeah. So,
was that the practical implications teased at the beginning of the talk?
Mm-hmm.
Okay.
Oh, well, no, there are other practical implications. I mean, given that we have the two things I wanted people to ask me questions about, machine engineering and medicine. Clearly, if we have a better understanding of the role of sense in biophysics, we must be informed in medicine. Just no question, right? We can actually explain how it is a particular sense forms in biophysics. Medicine is aided. In terms of machine engineering, if we understand this sufficiently, well, my favorite, because it's the most provocative idea, is that we can build machines that experience. Doing things, I have in mind making decisions across large-scale mathematical structures and doing things like recognition easily, which is something that biophysics does at very low cost. And the reason is because a recognition is essentially, there's no storage required in biophysics. So simply a reformation of structure. And so the whole processing system in terms of symbolic processing within biophysics is the formation of these structures, which you could consider symbols, and the hyperfunction connection to the response potentials that develop. So were you going to ask a question at the back? No? Okay. Yeah.
I'll stand by my comment about 5 months ago when I said I'm not qualified to review the book.
Well, yeah. New ideas are unfamiliar. And as a consequence, they're hard.
On a personal note, you really like 1 century ago.
I am very, yes, I've come to very much appreciate the work that was done in the formation of Harvard University around the work of Benjamin Peirce, his motivations, his interest. I don't agree with all of his politics, but he was of his time. And his sons undertook this was the mission that Benjamin charged his son Charles with. Build the bridge between pure mathematics and the physical sciences. And as a consequence, Charles made lots of great contributions to mathematical logic. He founded logic as semiotic theory, which is a terminology I'm dropping more and more because really it's logic as a natural science.
But it's not just that, it's also Turing.
Well, indeed. And then there's the whole, also Turing. I mean, Charles. Well, there's sort of a history of logic that extends into the 20th century from the 19th century, and Charles Peirce and his students fought against what they described as the Russellization of logic, which is basically the pursuit of the logicist agenda, in which logic ceases to be ceases to play the role that Benjamin wanted, but becomes a pure mathematics.